So just a rough sketch of these two lines. One might look like so, and the other one like so. So this is if these two lines are the graphs of these two equations, then this point here is the one unique point of intersection of those two lines. In this dependent system, what we'll see is that these two equations actually represent the same line. Let's see what that looks like when we are dealing with matrices. So the coefficient matrix will be -1, 3, -10, 2, -6, 20. I'm going to put that into my calculator. I'll use matrix C, I guess. I'm going to go ahead and edit matrix C. This is again 2 rows, 3 columns, -1, 3, -10, 2, -6, 20. All right, so I've got the matrix in. I'll exit out. Now let me go ahead and back to the matrix menu. I would like to find the reduced row echelon form button, and I will plop my matrix C right in there. Hit enter, and here's what I get. So the reduced row echelon form of the matrix is 1, -3, 10, 0, 0, 0. So notice we got a whole row of zeros. Let's translate that back into an equation to see what that actually means. So this tells us 1x minus 3y equals 10. And the second equation tells us 0x plus 0y, which is 0, equals 0. So imagine that if we had done the elimination method, you add the two equations together and you get a true statement out like this. Something like 0 equals 0, which is true no matter what. When that happens, we know we have a dependent system we'll have infinitely many solutions. And they're all going to be given by this equation here. X minus 3y equals 10. And if you like, you can rewrite that by solving for y, putting it in y equals mx plus b form. I'll subtract 3 from both sides, or subtract x from both sides and divide by a -3. This will give me y equals 1/3 x minus 10/3. So then the infinitely many solutions will all be of the form, whatever x is, y will be 1/3 x minus 10/3. This represents all of the points in the plane. They're all going to lie on a line that make this equation true. Now let's see one last case here. X minus 2y equals 3, and -3x plus 6y equals -11. What you might notice is that these two equations are two linear equations that have the same slope but different y-intercepts. So you might notice here that we're dealing with parallel lines. They never intersect, so there will be no solution. But suppose you didn't notice that by looking at the equation and you wanted to use the matrix capabilities of your calculator. So let's make the coefficient matrix 1, -2, 3, -3, 6, -11. Let's put that into our calculator. I'm going to go ahead and edit matrix A again. This is a 2 by 3 matrix, 2 rows, 3 columns. 1, negative 2, 3, negative 3, 6, 11. Let's exit out and then go back to the matrix menu, find the math operation REF, and I will plop the matrix A right in there. And here's what I get. Not a whole row of zeros, but this second row is 0, 0, 1. So let's write this down. Putting it in reduced row echelon form, we get 1, negative 2, 0, and 0, 0, 1. So what this tells us, this first row here says x minus 2y equals 0, which is a perfectly fine equation. The second equation says 0x plus 0y, which is 0, equals 1. And that is a false statement. So that tells us that we've got an inconsistent system, and we have no solution. All right, so these are our 3 possibilities. No solution happens when you have a row with like all zeros and then a number here, because that's going to give you a false equation. A dependent system, and again, this is where you have 2 lines that are actually the same exact line. And what that looks like is an entire row of zeros, which is the true equation, 0 equals 0. And then best case scenario, you have 2 lines that intersect in exactly 1 point where you have, here's the augmented part of the matrix, the number part, and the other part of the matrix has 1s down the diagonal and 0s everywhere else. In that case, it's a consistent system. You've got exactly 1 solution.